Okay, next problem is the energy level of an oscillator with frequency nu is given by when a system consisting of n independent oscillators has the total energy E equals to half n h nu plus m h nu, where m is an integer find the thermodynamic weight we say W weight is W m and determine the relation between the temperature of the system and energy E. So, problem number 5 states the energy level of an oscillator with frequency nu is given by epsilon equals to half h nu, 3 by h nu, 3 by 2 h nu and so on, when a system consisting of n independent oscillators, such oscillators has the total energy E equals to half n h nu plus m h nu, where m is an integer. Find the thermodynamic weight W m and determine the relation between the temperature of the system and E. Now, we discuss the solution. If the quantum number of the ith oscillator is denoted by Ni and E equals to half n h nu plus m h nu, implies that n1 plus n2 plus n3 up to nn gives m. Therefore, the thermodynamic weight of a macroscopic state with the total energy E is equal to the number of ways of distributing M white balls among n labeled boxes, right. So, we are assuming like that. Okay. So, Wm weight is m plus n minus 1 factorial by m factorial times n minus 1 factorial. This is the weight of the distribution. Now, second part we will discuss now. Now, S is entropy, S is KBln Wm, right, that we know. So, substituting the value of Wm, and using Stirling's approximation, under the assumption that both n and m are much greater than 1. So, we can write S is now the statistical temperature TE is given by so temperature is related to temperature can be expressed by 1 by T equals to del S by del E, and then if we further proceed, we get 1 by T equals to del S by del M times del M by del E, and so we get 1 by T equals to Kb ln m plus n by m del m by del e. Okay, so, if we differentiate S with respect to m, we get del S by del m is Kb ln m plus n by m. Okay, so, we get 1 by T equals to Kb by h nu ln m plus half n plus half n by m plus half n minus half n. Okay, now, so if we further proceed, we get 1 by T equals to B by h nu ln E by n plus half h nu by E by n minus half h nu. Okay. Or you can write or inversely write E plus half n h nu by E minus half n h nu equals to e to the h nu by kBT. So, solving this for energy, one gets or we get E equals to n times half h nu plus h nu by e to the h nu by kBT minus 1. So, this is the solution of problem 5. Now, problem 6 is there are 1000 molecules of an ideal gas in a box of 1 liter volume. So, there are 1000 molecules of an ideal gas in a box of 1 liter volume, assuming that the particles do not preferentially occupy any region, find the probability of finding the particles in a particular region of volume 100 centimeter cube. For what value of n where n is the number of particle, or number of molecules, is this probability maximum. So, problem number 6 is a conceptual problem. So, suppose there are 1000 molecules of an ideal gas in a box of 1 liter volume. Assuming that the particles do not preferentially occupy any region, find the probability of finding the particle in a particular region of volume 100 centimeter to the 3, for what value of n, n is the number of molecules, is this probability maximum? The probability, now we discuss the solution. The probability of finding a molecule in a volume of 100 centimeter cube is nothing but 110, right, because we have a box of 1 liter volume. So, the probability of finding a molecule in a volume of 100 centimeter cube is 1/10. If n particles, if n number of particles are to be there, the probability is is 1/10 to the n, right. Now, we had 1000 particles. Out of 1000 particles, n particles are present in a volume of 100 centimeter to the 3. Okay. So, the remaining (1000 minus n) number of particles or molecules must be in the residual volume of 900 centimeter to the 3, having a probability of 9/10 to the 1000 minus n, right. Hence, the probability of finding a particular set of n molecules in 100 centimeter to the volume is 1/10 to the n times 9/10 to the 1000 minus n, right. Since we can choose n molecules out of 1000 molecules in 1000 Cn different ways, the probability of finding the particles in a particular region of volume 100 centimeter to the 3 is so, this is the probability of finding the particles in a particular region of volume 100 centimeter to the 3. Now, if you take log of both sides, we get so if you take log of Pn, we get ln Pn equals to ln 1000 factorial minus ln n factorial minus ln 1000 minus n factorial minus n ln 10 plus 1000 minus n times ln 9 by 10. If we further simplify, get ln Pn equals to ln 1000 factorial minus ln n factorial minus 1000 minus n ln 1000 minus n, and ln n factorial we can further simplify like n ln n plus n, and then we have plus 1000 minus n minus n ln 10 plus 1000 minus n times ln 9 by 10. So, we are using Stirling's approximation here. Okay. So, now if we differentiate, because we need to get maximum probability, so we need to differentiate the above expression or Pn with respect to n, and then if we make it 0, we get the maximum probability. Okay. So, d ln Pn by dn equals to minus ln n plus 1 plus ln 1000 minus n plus 1 minus 1 minus ln 10 minus ln 9 by 10. So, we get d ln Pn by dn equals to minus ln n plus ln 1000 minus n minus ln 9, or we can get, or if we simplify further, we get d ln Pn by dn equals to ln 1000 minus n by 9n. So, for maximum Pn, for maximum probability Pn, ln 1000 minus n by 9n equals to 0 equals to ln 1. So, we get 1000 minus n by 9n equals to 1, get n equals to 100, n equals to 100. So, this problem is based on the concept of probability, and it is bit tricky problem, but it is doable. Okay. So, now we discuss problem number 6. Problem number 6 is the 3 lowest energy levels of a certain molecule are U1 equals to 0, E2 equals to epsilon, and E3 equals to 10 epsilon. Okay, the 3 lowest energy levels of a certain molecule are E1 equals to 0, E2 equals to epsilon, and E3 equals to 10 epsilon. So that at sufficiently low temperature, only E1 and E2 are populated. Find the average energy E of the molecule at temperature T and the contributions of 3 levels to molar specific heat CV, molar specific heat CV bar. Plot CV versus absolute temperature T. So, problem number 6 says the 3 lowest energy levels of a certain molecule are E1 equals to 0, E2 equals to epsilon, and E3 equals to 10 epsilon. So that at sufficiently low temperature only energy levels E1 and E2 are populated. Also find the average energy E of the molecule at temperature T and the contributions of 3 levels, 3 energy levels to molar specific heat CV bar. Plot CV bar versus absolute temperature T. So, we discuss the solution now. Let n, capital N, be the number of particles in the system. So, we have a system of capital N number of particles. So, N equals to N1 plus N2 plus N3, if we consider that there are only 3 energy levels of a molecule. Okay. Okay, so, considering only 3 energy levels E1, E2 and E3 are available. So, what is N1? N1 is the number of particles in energy level E1, E2 is the number of particles in energy level E2 and N3 is the number of particles in energy level E3. Okay. And now, N2 by N1 is E to the minus epsilon by kBT, right? Because, okay, so we'll just explicitly write what we are doing here. Okay, so N1 by N is e to the minus beta E1 by Q. Q is the partition function, and N2 is e to the minus beta E2. N2 is e to the minus beta E2 by, or N2 by N is e to the minus beta E2 by Q. Okay. So, N1 by N2 is e to the minus beta E1 minus E2. So, if we substitute the value of E1 and E2, we get e to the plus beta epsilon, or you can write N2 by N1 is e to the minus beta epsilon, or you can write e to the minus epsilon by kBT. Similarly, N3 by N1 is e to the minus 10 epsilon by kBT. Okay. So, from here we get value of N2 is N1 times e to the minus epsilon by kBT, and from here we get value of N3 is N1 times e to the minus 10 epsilon by kBT. Now, N1 plus N2 plus N3 equals to N. So, if we substitute value of N2 and N3 here, we get N1 plus, the value of N2 is N1 times e to the minus epsilon by kBT, plus the value of N3 is N1 e to the minus 10 epsilon by kBT. Okay. So, this is the expression we have got, and if we further simplify, we get value of N1 is N by 1 plus e to the minus epsilon by kBT plus e to the minus 10 epsilon by kBT. So, this is the value of N1. So, if we substitute the value of N1 into the expression of N3, we get N3 equals to, so N3 equals to N times e to the minus 10 epsilon by kBt by 1 plus e to the minus epsilon by kBt plus e to the minus 10 epsilon by kBt. So, if we further simplify, we get N3 is n by e to the 10 epsilon by kBt plus e to the 9 epsilon by kBt plus 1. So, when T is very low, T is T is very low, okay, then N3 goes to 0, right, because T is very low. So, in the denominator we have 10 E epsilon by kBt term. So, when T is low, these values are very high. So, we get N3 is very small or close to 0. So, it says only U1, only the energy levels U1 and E2 are populated. Populated at low temperature. So, this low temperature we call TC, on critical temperature. Okay. So, TC satisfies the equation n by 1 plus 9 epsilon by kb times Tc. Okay. So, we have the epsilon sign here. So, we have n by 1 plus e to the 9 epsilon by kBt plus e to the 10 epsilon by kBt, and we consider that, okay, so the lowest possible particle is 1. So, at critical temperature Tc there is only one particle in level 3, and below Tc there is practically no particle. Okay. So, it says below Tc, see, N3 goes to 0. So, at Tc we get this expression. So, if n is very large, then n equals to e to the 10 epsilon by kBt. Okay. So, and T here is Tc. So, Tc is 10 epsilon by kb ln n. So, this is the threshold temperature or critical temperature. So, average energy now we calculate average energy of the average energy, if we say this is E average. So, E average is epsilon times e to the minus epsilon by kBt plus 10 to the 10 epsilon by kBt by 1 plus e to the minus epsilon by kBt plus e to the minus 10 epsilon by kBt. This is very easy to do it. So, you consider the partition function. Okay. So, once you get the partition function, you can easily you differentiate the partition function with respect to temperature or beta at constant n and v, and you get the average energy, and this is the average energy expression. Now, specific heat, molar specific heat we need to calculate. So, molar specific heat we call molar specific heat is as Cv bar, so Cv bar is nothing but Na del E average by del T at constant volume. Okay, so, get if we carry out the differentiation, we get Cv bar is, so Cv bar is R epsilon to the 2 e to the minus beta epsilon plus 100. So, okay, so we get Cv bar R epsilon to the 2 times e to the minus beta epsilon plus 100 e to the minus 10 beta epsilon plus 81 e to the minus 11 beta epsilon times beta to the 2 by 1 plus minus beta epsilon plus e to the minus 10 beta epsilon to the 2. So, this is the value of molar specific heat or Cv bar. Okay, so, for low temperature, means when kBT is much smaller than epsilon, we get Cv bar so, we get the value of or the expression of Cv bar is R epsilon to the 2 e to the minus epsilon by kBT by kBT to the 2. So, if we plot now Cv bar versus temperature, absolute temperature. So, this expression of Cv bar at low temperature contains one decreasing function of temperature and another increasing function of temperature. Okay. So, it will pass through a maximum. So, you get like this. Okay, so, this is a very good problem. Now, problem number 7 we discuss. We will discuss now problem number 7. So, problem number 7 is for a monovalent ion which by definition gives 1 electron calculate the value of Fermi energy epsilon f given the number density value (10 to the minus 29 meter to the minus 3). Okay, so we need to calculate the Fermi energy of an electron, and number density is given. So we know the expression of Fermi energy. Okay, so Fermi energy epsilon f is h cross to the 2 by twice me for electron 6 pi to the 2 by 2s plus 1 times n by v to the 2 by 3. So me is the mass of electron, and the mass of electron is 9.1 times 10 to the minus 31 kg, and n by v is also given 10 to the minus 29 meter to the minus 3. Okay, and s is half, so 2s plus 1 gives 2, right. Now, if we substitute all here, we get epsilon f equals to 6.626 times 10 to the minus 34 to the 2 by 8 times 3.14 to the 2 times 9.1 times 10 to the minus 31 times 6 times 3.14 to the 2 by 2 times 10 to the minus 29 to the 2 by 3, and you get the answer in, since we consider all here in joule unit, so you consider the answer in joule. Okay. So the next problem, problem number 8, is consider a free electron gas at 0 Kelvin temperature and so that the de Broglie wavelength associated with an electron is given by lambda f equals to 2 times pi by 3 NO to the 1 by 3, where N naught is the number of electrons per centimeter to the 3 of gas. So, problem number 8 says consider a free electron gas at 0 Kelvin temperature and show that the de Broglie wavelength associated with an electron is given by lambda f equals to 2 times pi by 3 n naught to the 1 by 3, where n naught is the number of electrons per centimeter to the 3 of gas. Now, the solution. The momentum P of the electron is given by P is root over twice MEF, and we have EF at 0 temperature at 0 Kelvin equals to to the 2 by twice m e 6 pi to the 2 by twice s plus 1 times n by v to the 2 by 3, and twice s plus 1 for electron is 2, right. So, we get EF is h to the 2 by 8 m e 3 n by pi v to the 2 by 3. So, the de Broglie wavelength lambda f is h by p. So, we get lambda f is h by root over twice m e times E f. So, get lambda is h by root over twice m times h to the 2 by 8 m e where m e is the mass of electron times 3n by pi v to the 2 by 3. So, you get lambda is h by root over h square to the 4, h square by 4, 3 n by pi v to the 2 by 3. And if we further simplify, we get lambda is h. If we h and h they get cancelled, so we get 1 by half 3n by pi v to the 1 by 3. Okay, so we get lambda f equals to twice pi by 3 NO to the 1 by 3 proved. Okay, so we have proved it. So, next we discuss problem number 9, which is again a conceptual problem. It says a system of two energy levels E naught and E1 are populated by n particles at temperature T. The particles populate the energy levels according to the classical distribution law. Derive an expression. Problem number 1 is derive an expression for the average energy per particle Problem number 2 is compute the average energy per particle versus the temperature, the absolute temperature as T goes to 0 and T goes to infinity. And problem 3 is derive an expression for the specific heat of the system of n particles. And problem 4 is compute the specific heats in the limits T goes to 0 and T goes to infinity. So, problem number 9 says a system of two energy levels E0 and E1 are populated by n particles at temperature T. The particles populate the energy levels according to the classical distribution law. Derive an expression for the average energy per particle. This is the first problem. Second problem is compute the average energy per particles versus the absolute temperature as T goes to 0 and T goes to infinity. Problem number 3 is derive an expression for the specific heat of the system of n particles. And problem number 4 is compute the specific heats in the limits T goes to 0 and T goes to infinity. So, here is the solution. Problem number 1 is the average energy of the particle is if we say E average is E naught e to the beta epsilon plus E1 e to the minus beta E1 by e to the minus beta E naught plus e to the minus beta E1. So, this is the average energy. Now, assuming both E1 is greater than E naught and E naught is greater than 0 and delta E is E1 minus E naught. Delta E is the difference between the two energy levels. So, you can write average energy E is E naught plus E1 e to the minus beta delta E by 1 plus e to the minus beta delta E. So, this is the expression for average energy, very easy. Then next problem is when T goes to 0 means when beta goes to infinity. Okay. So, T goes to 0 means beta goes to infinity. So, average energy E bar equals to E naught plus delta E or E naught plus E1 e to the minus beta delta E times 1 minus e to the minus beta delta E. Okay. So, we get E naught or E average is E naught plus delta E e to the minus beta delta E. So, this is the value of average energy when T goes to 0. This is when T goes to 0. Now, next is when T goes to infinity. When T goes to infinity means beta goes to 0. So, average energy is half times E naught plus E1 minus beta E1 times delta E times 1 plus half beta delta E. So, we get E naught or E average equals to half times E naught plus E1 minus beta by 4 delta E to the 2. This is when this is the expression for average energy when T goes to infinity. Now, problem number 3. We need to calculate specific heat. Okay, the specific heat per mole is C equals to NA del E average by del T. So, get C, or you can go specific heat per mole, you consider C bar actually. So, C bar is Na del E average by del beta times del beta by del T. So, we get C average is R times delta E by kBT to the 2 times e to the minus delta E by kBT by 1 plus e to the minus delta E by kBT to the 2. Okay, so, this is specific heat per mole, and the last one, problem number 4, is we need to consider the temperature limits. So, when T goes to 0, C bar is R times delta E by kBT to the 2 e to the minus delta E by kBT. And when T goes to infinity, C bar is R by 4 delta E by kBT to the 2. Okay, so, we considered both the limits when temperature goes to 0 and temperature when temperature goes to infinity, and we calculated specific heat per mole. Thank you.